So angular momentum is the moment of linear momentum of an object. All right. Now, as you can see right here, moment is the point where the object is turning or rotating. So at this point is our moment or pivot. As you can see right here, the object is moving around the points. Okay, what you are seeing here is called angular momentum. It is the moment of linear momentum, and the symbol we use to represent angular momentum is capital L. Is capital L. We use L to represent angular momentum. Now, let's look at the formulas we have for angular momentum. It is L equal to linear momentum, which is mv, times the what? The perpendicular distance from the axis of rotation, which is this. Look at this. Here is the perpendicular distance from the what? Axis of rotation. So therefore, the formula for angular momentum is mvr. M is the mass of the object, v is the speed or velocity, while r is the radius or the perpendicular distance from the axis of rotation. Now guys, if you recall, in linear and angular velocity, we said that v is equal to rw, where r is the radius and w is omega, or is the angular velocity. With this formula, I can derive a new formula or a next formula for angular momentum. So therefore, I can say my angular momentum L is equal to the mass, the V becomes RW times R. So I replaced my V with RW. So therefore, I can say that my angular momentum L is equal to M. R times R is R squared times what? W. Here is our second formula we use for solving angular moment. Why this is our first formula for solving angular momentum. It's our first equation, and here is our second equation for solving angular momentum. Now I can derive a third formula from this equation, because I know that moment of inertia, which is given as I, is given as capital I, is equal to mr squared. Here is the formula for moment of inertia, which is this, mr squared. So therefore, I can take this off and replace mr squared with what? With moment of inertia. So therefore, I can say that my new formula for angular momentum is L equal to, I can take this off, becomes moment of inertia times my W, which is my angular velocity. So here is my third equation for angular momentum. And please note that the units for angular momentum is kilogram meter squared per seconds. This is the units for angular momentum. And my m is the mass of the body or object. The v is the speed or linear speed of the object. R is the perpendicular distance. From the axis of rotation W or omega is the angular velocity, and I is the moment of inertia. It is measured in kilogram meter squared. It is measured in kilogram meters squared. So these are the different parameters that we can use to solve angular moments or angular momentum of an object. Please, we can use any of these three equations to solve questions on angular momentum depending on what is given to us in the question. Now, what you see here on your screen are the moment of inertia for different shapes. Different shapes as a moment of inertia. All right? So you can see right here that the moment of inertia for a rod which is rotating at one end is ml squared over 3. The m here is the mass. The m you are seeing right there is the mass of the object, while the L is the length of the rod. Okay? The m is the length of the rod or object. Okay, so guys, please note these, and very important to always remember this table. It's very important in solving questions that involves angular momentum. All right? Sometimes when you are given a question, you might be asked to extract one of these formulas or one of these moment of inertia for a given shape. So please take note of these different shapes and their axis of rotation and their moment of inertia. With these, we can solve questions that involves moment of inertia that is connected to angular momentum. Let's look at a question here, please. It says, what is the angular momentum of a thin rod rotating about one end? Please note this word. At 150 rads per second. This is my angular speed. So I can call my angular speed omega is 150 rads per second. With a mass of 4 kilogram, my m is 4 kilogram. And is 7 meters long. So the rod is 7 meters long. The length of the rod is 7 meters long. We are asked to find the angular momentum, which is what? Capital L. And if you remember, the formula I can use to solve this question would be angular momentum equal to inertia times my angular speed. Now, the inertia of a rod rotating about one end is, on my table here, a rod that is rotating about one end is what? Is ml squared over 3. This is the formula I will use to get my moment of inertia for a rod that is rotating about one end. So I can say that my inertia is equal to mL3 or 2 over 3. With this equation, I can calculate the moment of inertia for that rod, and I will put this in my formula to get my angular momentum. Please remember again, we are asked to find the angular momentum of a thin rod rotating about one end. That means that step 1, I have to find the moment of inertia of the rod that is rotating about one end, and the formula to use is this formula right here. This formula. Okay, so what next? I can log in my data. My mass is 4 times my length of the rod is 7 squared over 3. So therefore my moment of inertia is given as what? That will give us 65.3 kilograms meters squared. So now I can find my angular momentum by logging in the different values. So my angular momentum L is equal to my inertia, which is 65.3 times my angular speed, which is 150. So we can multiply these together, and that gives us what? That gives us 97 what? So this gives us 9795 kilogram meter squared per second. So here is our final answer to this question. Now, to solve this question, you must take notes of the coordinate system. This affects the position or the sign of our speed. As you can see in this case, it says the mass is m is 0.12 kg. Our speed v is 0.56 meters per second, and our r, our radius, is 0.25. Is 0.25 meters. To solve this question, we use what? Angular momentum equal to mvr. But we must note something here. It says if the coordinate system counterclockwise is positive, that means the speed is moving what? Clockwise. As you can see right here, moving clockwise is the speed. It says if the coordinate system is what? Positive. That means when you counter this speed, it is what? Positive. If here is positive, it means that my speed will be what? Will be negative. Look at this, please. If the coordinate system counterclockwise is positive, it means that my speed will be what? Will be negative. Will be negative. So my speed will be negative. That means our answer will be a negative answer. So always pay attention to the coordinate system to determine the sign of your speed. So therefore I can say that my angular momentum is mass is 0.12 times my speed, which is minus 0.56, times my r, which is 0.25. So with this, we can say that our angular momentum is equal to minus 0.0168 kilogram meter squared per second. So this is our final answer for this question. It says a disk of inertia. So my inertia is I. My R is 0.85 kilogram meter squared. It's rotating counterclockwise with a speed. My omega is 15 rads per second. And we're asked to find the angular momentum of the disk about its center, which is my L. Okay, now we are asked to answer using what? A coordinate system where clockwise is negative. If it's negative, that means that my speed will be what? Positive. So therefore I can use the formula, which is angular momentum equal to inertia times my omega. Please, I repeat this. The reason why my omegas or my angular speed is a plus is because the clockwise is negative. Because the clockwise is negative and my speed is moving anti-clockwise, so therefore my speed will be what? The opposite of this. So it becomes what? Positive. So therefore my inertia is 0.85 times my positive 15. So therefore my angular momentum is positive 12.75 kilogram meter squared per second. Please, it is always important as a student of engineering or science student to always write your answers or your values with the correct units. So this is our final answer to this question. The principle of conservation of angular momentum states that if no external forces is acting on the system, the total momentum of the system is the same or remains the same. This means that this is saying, in other words, is saying that the initial momentum or the initial angular momentum is equal to the final angular momentum. So this is the principle of conservation of angular momentum. It states that if no external forces is acting on the system, it means that the total momentum of that system is the same. In other words, the initial angular momentum is equal to the final angular momentum. Now, this is similar to the linear momentum. Now, if you recall, I gave us three formulas earlier where I said that linear angular momentum L is equal to mvr. Now, for To apply this principle to this equation, we are saying that the initial angular momentum Li is equal to the final angular momentum Lf. That means that for the initial angular momentum, with this formula, to be what? M1 Vi Ri equal to Mf final Vf final times Rf. So here is a formula we can use for the principle of conservation of momentum. Also, we said that angular momentum L is equal to mr squared omega. We can also apply this using the principle of conservation of angular momentum. It becomes mi ri omega I equal to mf rf omega f. Here is a next formula we can use to solve the principle of conservation of angular momentum. Also, we said again that angular momentum is equal to moment of inertia times the angular velocity. We can also apply this using the principle of conservation of angular momentum. It becomes I subscript I omega I equal to I subscript F omega F. So guys, these are the different equations we can use to solve for the principle of angular momentum, which states that the initial angular momentum is equal to the final angular momentum. Please remember that our m is the mass, the v is the velocity, the r is the perpendicular distance from the axis of rotation, our omega is the angular velocity, our I is the inertia. Please don't forget that our R is squared, and what? Squared. Now, this question is very, very easy, but we have to identify the initial angular momentum and the what? The final angular momentum. So I'll start with the initial. The initial angular momentum for the mass, our mass is m, so the mass is m, our mass mi is m, okay? Rotate with a speed of VO, so our VI for initial is VO, okay? For a point on each surface at a distance of 2r, so my Ri is 2r, okay? Now, for the final angular momentum, our MF is, it says the star collapses to radius r, but the mass remains the same. So my MF is same thing as my initial mass, which is m. My RF is r. It says the star collapses to radius r. So from 2r, it becomes r. So it's r. we are asked to find the final speed. Find the final speed. So my VF is V. So find the final speed. What do? The formula remains the same. The initial angular momentum is equal to the final angular momentum. Okay? So I can use the formula, which is my M I V I R I equal to my M F V F equal to R F. Good. So my M1 is M, my V1 is VO, V subscript O, my RR is 2R, is equal to, my MF is M, my VF is V, my RF is R. Now what next? We can make our V the subject because we are asked to find the final speed V. So therefore, I can divide both sides by MR. Divide by MR. I will divide by MR. So M cancel M, R cancel R. So my V is equal to, this way my M cancel M, my R cancel R. So I am left with what? 2 V subscript O. So this is my final speed. And question again, we are asked, how does it compare to its initial speed? As you can see right here, the final speed is 2 times the initial speed. That means it is faster than the initial speed. So this is how we solve such a question. So we are asked to find, it says a point on the edge of a satellite with mass 50 kg. So my initial mass is 50 kg. And the speed is 10. So my V1 initial speed is 10 meters per second. And the distance 3 meters RI is 3 meters from the central axis of rotation. It says the satellite unfolds its panels, increasing its radius to 6 meters. So the final angular momentum, which is RF, is 6 meters. But the mass remains the same. So my MF is still 50. What is the final speed of a point at the edge of the satellite panel? So my VF is not known. My VF is not known, okay? So the formula is the initial angular momentum is equal to the final angular momentum. This becomes M1, MI, VI, RI equal to MF, VF times RF. So we can log in the data. My M1 is 50. 50 times my V1 is 10 times my R1 is 3 equal to my MF is 350. My V is VF. My RF is 6. So therefore, this will give us 1500 equal to 6 times 50 is 300. We have 300 VF. So what next is that we divide both sides by 300. So divide by 300. I divide by 300. 300 cancel 300. Therefore, my VF, or my final speed, is equal to 1500 divided by 300 gives us 5. That is 5 meters per second. Good. Now, it says, how does it compare to the initial speed? From this, we can say that the final speed is half of the initial speed. So I can write it out. The final speed is half of the initial speed. So that is our final answer. So the final speed is 5 meters per second, and it is half of the initial speed. Final answer.